Hello. I'd like to spend some time with you today talking about L'Hopital's rule, a rule in calculus that helps us compute limits of ratios of functions. It also appears as ratios of products of functions in certain circumstances, but we're going to kick back to this circumstance as we can. So it says that the limit as x approaches a of f over g is equal to the limit as x approaches a of f prime over g prime. And I wanted to write that up there right away from the beginning here, and then make the immediate qualification that says only if we have indeterminate form of 0 over 0 or infinity over infinity. If we don't have indeterminate form for this limit, then this equality fails to hold. Right? So it's only good if we have indeterminate form. So as we do limits, one of the things that we're going to do first off is we're going to check whether we actually have the indeterminate form 0 over 0 or infinity over infinity. I guess I should put positive negatives on these as well. Yeah. So the first thing that we're going to do when we're approached with this limit here, which we could solve using some techniques that we did in Chapter 2, namely we'd introduce an x, and then we'd use two identities that we used earlier. So the first thing that we're going to do is check that we actually have indeterminate form. So if we try to plug in 0 to this thing right here, I've got cosine of 2 times 0, which is just 0. Cosine of 0 is 1. Cosine of 0 is 1. Yep, that's still true. So we have 1 minus 1 over sine of 0 is 0. So we really have 0 over 0. So we have the right indeterminate form. All right, so we try substituting in, and we got this nonsensical thing 0 over 0, which we just can't work with it by itself. We've got to do something to transmute it. So we've got this indeterminate form. So we're going to invoke L'Hopital's rule. So when I invoke L'Hopital's rule, I'm going to be careful to name the theorem and say why I can justify what I'm doing when I do it. So I'm going to say by L'Hopital's rule, this thing is equal to the limit as x approaches 0 of the derivatives, the ratio of the derivatives of those two things, right? I'm not taking the derivative of this expression. I'm taking f prime over g prime. I'm taking the derivative of each of those two things separately. So I'm not taking the quotient rule here because I'm not taking the derivative of this expression. So let's take the derivative of the top. I'm going to have minus 2 times sine of 2x. And on the bottom, I pick up 5 times cosine of 5x. And if I now try to substitute in to this expression my zeros, so I'm going to try to sub, right? So I'm going to have minus 2 times sine of 2 times 0 over 5 times cosine of 5 times 0. Sine of 0 is 0, and cosine of 0 is 1, so that's just 5. And 0 over 5 is just the number 0. So we evaluated this limit, and it is in fact 0, which is the exact same thing that you would get if you were to evaluate that limit by introducing an x and playing some other little algebraic tricks with it. L'Hopital's rule is pretty cool because it makes doing some of these limits basically trivial. The only caution really, I think, is... I think there are two big cautions when doing L'Hopital's rule. The first big caution is make sure you have indeterminate form before you go applying L'Hopital's rule. Because if you don't have indeterminate form, then you just get nonsense. You don't want nonsense, do you? I don't want nonsense. The second major caution is don't use the quotient rule in this case because we're not taking the derivative of the function, we're taking the limit of. We're doing this tool, which is really all about racing rates of change, and I'm not going to explain what that is in the context of this video. I'm sorry. So let's do another example. Let's do the limit as x goes to infinity of x squared over e to the x. First thing that we're going to do when we try to evaluate this limit is just plug the thing in. Okay. So we're going to plug in, and I've got infinity squared, which is infinity, and I've got e to the infinity, which is infinity. So I've got the flavor infinity over infinity, indeterminate form. Great candidate for doing L'Hopital's rule. So we'll do L'Hopital's rule. So this thing is equal to the limit as x approaches infinity of the derivative 2x over the derivative e to the x. And I try plugging in x equals infinity, and I get indeterminate form infinity over infinity again. But that's no problem, because I can just be all like L'Hopital's rule. And this is equal to the limit as x approaches infinity of 2 over e to the x. And now I'm going to plug in my infinity to this. Numerator stays as 2 over infinity. 2 over infinity, in this case, this is positive infinity. So that's equal to 0. We've got some fixed numerator and some denominator, which is growing without bound. So it's going to go to 0. Pretty sweet. Another way to approach this this limit would be to realize, okay, well, the numerator is a polynomial, and the denominator is an exponential. And exponentials go to infinity way faster than polynomials. So in terms of relative rates of change, this one's going to go to infinity way slower than this one. So it's going to be like a smaller infinity in some sense on the top. And it's going to work out to go to 0. All right, let's do one more derivative with L'Hopital's rule. Let's do the limit as x approaches negative infinity of, no, I want to do 2 more, of x times sine of 1 over x. So let's try. So we've got a limit. So let's try evaluating this thing. So if we just try plugging in, we're going to have minus infinity times. Okay, so this thing here goes to 0. The 1 over x part goes to 0 as x goes to negative infinity. So it's going to be like times sine of 0, which is 0. So we've got like negative infinity times 0. That's not one of these two forms for indeterminate form. So we can't apply L'Hopital's rule to it. So what we're going to do instead is we're going to rewrite this so that it's in a form where I can apply L'Hopital's rule. So I want to get it into either 0 over 0 or infinity over infinity. And so I can either try to like move x into a numerator or denominator or sine into a numerator or denominator. I think today I'm going to do it by going the limit as x goes to negative infinity of 1 over x to the minus 1 times sine of 1 over x. And now you might still be like, but we have times. And I'm going to be like, that's okay. I'm going to move my sine of x, sine of 1 over x, to the top here. So sine 1 over x. So let's try plugging in let's try plugging in minus infinity to this thing here. So I'm going to have sine of 0, which is 0 over, let's see here. So x to the minus 1 is shaped like that. Here's x to the minus 1 as it goes toward negative infinity. That goes to 0. Ooh. So now I've got my 0 over 0 indeterminate form. And I'm good to go for L'Hopital's rule. So let's take the derivative by our friend L'Hopital's rule. So this has to be equal to the limit as x goes to negative infinity. That part's not going to change. Now we're just going to take the derivative of these. So, I'm not taking the derivative of this thing, so there's no quotient rule. I'm taking the derivative of the numerator and denominator separately. So in the top, I'm going to have cosine of 1 over x times, now the derivative of 1 over x is minus x to the minus 2 over, take the derivative of x to the minus 1, and I'm going to have minus x to the minus 2. And now we'll simplify. So I've got minus signs in the numerator and denominator. So they're going to cancel. Ooh, and I've got x to the minus 2 in both the numerator and denominator. So I'm going to let those cancel also. Now I don't need my divided by bar. Ooh, this is pretty nice. So this is equal to cosine of 1 over minus infinity, which is cosine of 0, which is 1. Nice. Dig it. I like L'Hopital's rule. I think it's pretty cool. So let's do one more. There's one more that I wanted to get to because I think it's a valuable example to see. So one of the cautions with L'Hopital's rule is to be careful that you actually have indeterminate form. So let's consider the following example. Let's take the limit as x goes to 0 of cosine x minus sine squared x all over sine x. I'll give you a second to think about this function. Try plugging in 0, right? Try the just plug it in method for evaluating a limit. What do you get? Well, here's what I get. Cosine of 0 is 1. Sine of 0 is 0. So sine squared of 0 is still 0 over 0. That's 1 over 0. That's not indeterminate form, right? That's neither of these two things, right? This is some flavor of infinity. So we can't apply L'Hopital's rule to this thing, nor should we. We should just use our typical methods of computing limits to evaluate this one. So we don't have the appropriate indeterminate form to take L'Hopital's rule, so we're just going to do regular old limits on this thing. So let's go ahead and rewrite this so that I have cosine x over sine x minus sine squared x over sine x. I'm going to cancel that one out of the bottom there. And this cosine over sine expression is where my infinity is going to come from. So this term right here is going to go to 0. So we're going to ignore it. And this is just equal to the limit as x approaches 0 of cosine x over sine x. So it looks like 1 over 0. It looks like 1 over 0. Right? And it's tempting to want to be like, well, it's infinity, because that's what 1 over 0 is. But it's not quite that simple, right? So to the right of x equals 0, x is positive, and cosine of x is bigger than 0, and sine of x, in particular, so sine of x to the right is bigger than 0, so the limit as x approaches 0 from the right of cosine x over sine x equals positive infinity. But what about to the left? What about to the left? To the left, cosine of x is bigger than 0, but sine of x is less than 0. So I've got some fixed number over some negative, very small number. So the limit as x approaches 0 from the left of cos x over sine x is equal to negative infinity. So on one side, to the right, it goes to positive infinity, and on the other side, to the left, it goes to negative infinity. So we then conclude that this limit here does not exist. Doesn't equal, does not exist. It does not exist. Right. So in this particular case, we found that L'Hopital's rule didn't apply because we didn't have the right indeterminate form. And when we go and do the actual limit by examining stuff to the left and right, we reveal that the limit, in fact, does not exist. So good luck with your L'Hopital ruling, and I hope you have a lovely day. Bye.